Thank you. Welcome, everybody. If you can take your seats. Welcome to the last concluding talk of our Boole Shannon series. Some of you may have been following it all along. Some of you may be coming for the first time. This marks the 200th anniversary of Boole's birth, which was last year, and the 100th anniversary of Claude Shannon, which was this year. This lecture series has been run in conjunction among MIT RLE, MIT Physics, MIT ECS, and University College Cork. So thank you to all those entities for all the support they have provided. Today we're very fortunate to have Professor Sergio Verdu from Princeton. Sergio, I think, probably requires an introduction, but here he goes. He's a member of National Academy of Engineering, National Academy of Sciences, won the Hamming Award, has the Hamming Medal, has also won the Shannon Award from the Information Theory Society. More paper awards that you can shake a stick at. And also he has been lately working quite a bit on the life and scientific legacy of Claude Shannon. In that light, after the talk, there will be a reception for an IEEE milestone ceremony that we'll have a plaque. So we encourage you to join us in 34401. So for those who are not familiar, you go up the elevators that are to the left to the 4th floor and then follow the corridor all the way down. And in that vein, I'd like to recognize the fact that we have the children of Claude Shannon here. We're very honored to have their presence, and so they will be at the event. So with all that, welcome, Sergio.
Thank you so much. Pleasure to be here. This is like going to the Vatican to talk about St. Peter. So I'm gonna give you a chronological account of Claude Shannon's life. You know that April 30th was his the 100th anniversary of his birth. And well, without further ado, let's get started at day one. So Claude was born in the upper middle part of Michigan, in the town of Petoskey, but actually lived in Gaylord. Gaylord is a town which they call it the Alpine Village. Is very proud of its Bavarian heritage. It sits at the 45th parallel, and Shannon's family, actually here I have here a little notice from when he was born, says, Claude E. Shannon has received many congratulations this week over the arrival of a son on Saturday evening last. Mrs. Shannon's son are doing fine at Petoskey Hospital. And these are his parents, Claude Elwood Shannon, although our Claude never liked to use Junior on his name. So Claude came actually from New Jersey. He had Scottish ancestors, was born in Oxford. In fact, they were distant relatives of Thomas Alva Edison. And Mabel Wolfe, her parents actually were German, and they had migrated to Michigan right before she was born. And then here is Claude's elder sister, who was also very much interested in mathematics. And here there's a picture of Claude's parents. So Mabel, in fact, was, at some point, she became the principal of the high school in Gaylord. And she was also teaching languages. And at some point, she was fired from her job. Why? Because they decided that no female teachers who were married could continue being employed. So they had to give those positions to unmarried women. Claude Sr. Was involved in a variety of enterprises, real estate, furniture. He was also an undertaker at some point. And had a furniture store, and then also at some point he became judge. So here's a picture of the school, the elementary school, and here's our hero here, looking rather unhappy. And here's one of his talents, was to play musical instruments, as you can see here. And his father used to buy him these erector sets, and this piqued, of course, his interest in actually building gadgets. And he was saying that every time his father would go to the big city, he would bring him a bigger and bigger erector set. So here there is a letter that he wrote, as you can see, with MIT letterhead in 633. He said, I remember, in particular, a telegraph line we constructed running between, actually I have a bigger, between the Hutchin house and my house. And we also constructed radio-controlled boats, model airplanes, and the like with his friends. So already there, he was very interested in building stuff. And then he said, my interest in mathematics developed later while I was in college at Michigan and later at MIT. And today, this is 63, my interest is in the application of mathematics to electrical engineering, physics, and economics. So one of the things that Claude remembered reading when he was a child was this story by Edgar Allan Poe, The Goldbug, which many of you know at the end has a cryptogram that you have to decipher, and that's kind of like the centerpiece of the story. And of course, Claude eventually became one of the leading persons in cryptography. So he joined the University of Michigan. His father died when he was a sophomore, and then after that, he really had very little contact with his mother. So at the University of Michigan, he double majored in electrical engineering and in mathematics. And here's a picture of him as a freshman. And another thing that he remembered doing when he was at Michigan is taking a course on logic. And this is where the two heroes of this lecture series meet. And of course, we'll see what is the connection later. But this is one of the stuff that he remembers reading from that time. Another thing that he remembered reading from his undergraduate days is this paper that appeared in 1928 in the Bell System Technical Journal. This paper actually had a profound influence on Claude's thinking because it talks about the capacity of a system to carry information, the need to measure information. It has, I believe, one or two formulas only, so it's mainly a tutorial, but Hartley, who was actually one of the founders of Bell Labs, eventually received the IRE Medal of Honor in 1946 or 47. And in fact, in the citations, they say, because of his clear explanation of the capacity of a system, which is limited in bandwidth, to transmit information as a function of the duration of the message. So I guess he was an information theorist, you could say, before information theory. The first one to receive the IEEE Medal of Honor, and of course this year is also an information theorist, Dave Forney, who is receiving the highest award in the IEEE. And in between, we've had several others. We had Claude himself, we had Bob Gallagher, we had Viterbi, Jacobs, Kailath. So information theory has been one of the fertile grounds for medals of honor of the IEEE. So then he moved to MIT. As you can see here, this is how it looked at the time when Claude came here. It had just moved 20 years before from Boston to the other side of the river. And the reason why Claude came here was because in Michigan, he saw in a bulletin board, he saw an announcement for an opening to run a machine, was the differential analyzer, which was one of the most advanced analog computers of the time. So this machine could solve 6-order differential equations. And it was all done using Lord Rayleigh's method of integration. Claude was in charge of actually programming the machine. Someone would bring a differential equation. He would program the machine to then output the result in one of those tables. Those were like plotters where you could get the result. So here's actually the designer of that machine was Vannevar Bush, who I believe was Dean of Engineering here and then became one of the advisors of President Roosevelt, head of the Carnegie Institution, founder of Raytheon, very accomplished man with a lot of connections. And the fact that he was Claude's mentor actually played a very important role in Claude's professional life. So this machine had the analog side that you see here, but also had a control part, which was made out of relays. So Claude had to deal with that control part. And then it dawned on him that this course he had taken on logic, on Boole's logic, he could actually apply it to describe circuits with relays. And then he wrote his master's thesis. And this master's thesis has been described as the most important master's thesis of the century, or maybe ever. And it's really the beginning of computer engineering. It's really the first attempt to systematize and viewing this problem of designing relay circuits using mathematics, independent of technology. And that, of course, was a leitmotif in things that many of the things that Claude did later in life. So that thesis brought him quite a bit of recognition. So here you can see a notice from the New York Times when he got the Alfred Nobel Prize. This is the American Nobel Prize given to young engineers under the age of 30. Of course, sometimes there are funny misspellings. So here's a notice from Gaylord, who's somehow they miss the significance of that award. But then he also wrote another paper for the analog part. So he actually did similar analysis of trying to mathematize the differential analyzer. And in his own words, he said, this paper flew like a lead balloon. So it was not cited very much. So he went on, he was trying to focus on a PhD thesis topic, and it didn't come very quickly. So he was playing with some ideas here and there. And this is one very important correspondence he had with Vannevar Bush. And you can see here, this is February 39. And he says, off and on, I have been working on an analysis of some of the fundamental properties of general systems for the transmission of intelligence, including telephony, radio, telegraphy, television, and so on. So the idea that we can think of all these systems that in that point they see as being very different from each other, we're going to think of them in a unified way. In fact, this is already somewhat present. This kind of philosophy is already present in Hartley's paper, but there is a very important ingredient here that it was not present in Hartley's paper, and is that when Shannon thinks of these transmitters and receivers, he's not thinking about the usual design philosophy at that time, which was to design instantaneous rules. So, for example, AM or FM would just be an instantaneous processing, or even PCM, of the original message. What he does is different, because what he says is we're going to take we're going to take the whole waveform. We're going to observe the whole waveform, and on the basis of the whole waveform, we're going to output the transmitted waveform, and the receiver, again, is not going to be just a memoryless transformation. It's going to be a box that is going to look at the whole received waveform before guessing what this was. That, of course, is a very important idea in information theory. Okay, but this was not actually his PhD work. But before I tell you about the PhD work, here's a letter from the chair of the aeronautical department to the president of MIT. He says, well, we have 20 students who are enrolled for flying lessons. And I have talked to this fellow called Shannon, who is not only unusual, but in fact a near genius of most unusual promise. And then he says, since Shannon has not yet flown, he may be withdrawn without obligation to the government. Do you wish him to withdraw on the ground that any life risk, whatever, however small, is not justified in this case? So then the president of MIT responded and said, look, you know, if Mr. Shannon wants to get his license, there is nothing we can do about him. Let him get his license. If he ever says anything about joining the Air Force or anything like that, let me know and we'll take care of that. So yeah, he got his license, and then he did write his PhD thesis. This was in the math department. Sorry, the copy is so lousy here. This was April 1940, an algebra for theoretical genetics. So again, kind of like the master's thesis, he had introduced a formal mathematical tool to describe switching and relay circuits. So he was doing the same thing for Mendelian genetics, and he did that work in the span of a summer that he spent at Cold Spring Harbor in Long Island. It was a very brief thesis, and he never actually bothered publishing it. And then eventually people rediscovered some of these results and so on in the genetics field. So then he moved to this town in central New Jersey, Princeton. So his apartment was in Palmer Square. And the reason why he moved to Princeton was because he got a fellowship at the Institute for Advanced Study. And at that point, these are the people that were at the Institute. Here you see von Neumann, Einstein, Gödel. And this was actually Claude's mentor, Hermann Weyl. And the idea was, again, he was a very famous algebraist, and Claude said, you know, I have these ideas to apply algebra to all sorts of fields of interest in practice, so maybe we can do something. So Hermann Weyl, you know, heard about this person who was a genius from MIT, and so he was very, very happy to welcome him. But after 2 months, somehow Claude was not very happy, and he resigned from the Institute. And in fact, then moved to Princeton to work. This was already 1941, to work on the war effort. So there was this office called the National Defense Research Council, and they were doing computations of fire trajectories, trajectories of airplanes and so on. And apparently, the person who got him that job was a friend of Vannevar Bush by the name of Warren Weaver, which we will encounter again in the story. So while he was at Princeton, he wrote this letter. This is kind of like a progress report. You can see here it says fire control research. So he writes this letter to a professor of mathematics, who was in fact the dean of the graduate school in Princeton. And then he says, well, blah, 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 I've done work on differential analyzer and so on. Some new research was done on a general theory of information, of transmission and transformation of information. So this is really beyond that letter that he wrote to Vannevar Bush. This is the first time that we have written evidence that he was working along the ideas of what later would become information theory. All right, so he was in Princeton only for altogether a year, and then he moved to Bell Labs. And Bell Labs had this gigantic facility on West Street. That was, of course, the branch jointly owned between AT&T and Western Union, had been founded in the 1920s. And there was a lot of stuff going on here, of course, as you can imagine. They already had this philosophy of working on very advanced topics. But at that time, 1941, they were all concentrated on very specific problems having to do with the war effort. And in particular, the Manhattan Project had one of their branches was here in New York. So here you see Claude, where he lived in 51 West 11th Street. Here he was just 25 years old. And this was not a particularly happy period for Claude. He was, again, not really enjoying a lot what he was doing in Bell Labs. But his friends at the time were saying that he was spending the whole night working on his own stuff in his own apartment. And that sometimes he had trouble going to work to Bell Labs the next day because he had spent the whole night working on his own stuff. And of course, you can imagine what that stuff was. And here's another picture of him, also smoking, from 1944. Very distinguished looking. So progressively, as he had to do less and less work connected to those war problems, he also became very interested in, in the fire control problems. He also became very interested in cryptography. So he had quite a few conversations with Alan Turing, even though he said that they never really discussed cryptography. They were more discussing things like artificial intelligence. And also, Claude was using Alan as a sounding board for some of his ideas on transmission of information. And what he said was that most of the feedback he was getting from Turing was actually negative. So too bad about Alan, nobody's perfect. He actually, while he was in Bell Labs during the 40s, he didn't publish much, but he wrote some very important technical notes. In particularly this one, this is tremendously important because in this technical memo, he actually describes the optimal detector for signals in Gaussian noise. So North and Middleton had invented the match filter as a very simple solution to a maximal signal-to-noise ratio problem in radar, just using the Cauchy-Schwarz inequality. But what Claude did was much more profound because he showed that, in fact, the match filter was the best way to combat noise, Gaussian noise. And not only that, but he did it also assuming an arbitrary spectral density for the noise. So this memo is really the beginning of what we call digital communications nowadays. So traditionally, historically, people tend to attribute digital communications to Kotelnikov in the Soviet Union, but in fact, Shannon preceded that. But for some reason, he never published this paper. And then, 1945, he had his mathematical theory of cryptography paper. He was developing some of the notions that will later on be part of his 1948 paper in parallel with cryptography. So it's not like cryptography suggested the other one. But you do find the word entropy, for example, for the first time in the context of communications in this paper. So this was declassified eventually. I think it appeared eventually in the Bell System Technical Journal in 1949. But of course, this paper has the fundamental theorem of cryptography, which is that if you really want ironclad privacy, the key should be as long as the message. Unless the message is redundant, in which case you can get away with the entropy of the message. And that'll give you ironclad privacy, as opposed to, you know, what privacy nowadays is based on problems that we believe are computationally hard, although nobody is really sure. Okay, so then Bell Labs, they had been building this lab in New Jersey. This was the largest industrial lab in the world. And Claude was one of the last ones to move to Murray Hill. And here's an excerpt from the telephone directory in March 47. So MH, of course, stands for Murray Hill, and some of them still were in New York. So here was the big boss of the mathematics department was Hendrik Bode. And then under him, there were Darlington, Ditzold, Shelkunov, Schuhart, Tukey, John Tukey. And then under Ditzold, there were, the first person is always the assistant. And then there were three people, Richard Hamming, Brockway Macmillan, and Claude Shannon. So you know about Hamming, of course, the Hamming code, his contributions to signal processing. You may not have heard about Brockway Macmillan. He's still alive. He was, in fact, older than Claude. And he was a student of Norbert Wiener here, and extremely competent in ergodic theory and so on. And after Bell Labs, he in fact became involved in the Department of Defense. And at some point, he was the head of the National Reconnaissance Office that oversees all the spy satellites. All right, so another thing I want to point out here is the fact that you see this group here, then everybody in this group are actually female. These were called computers. So these people, they would bring them stuff to compute, and they were mathematicians, and one of them, Miss Mary Elizabeth Moore, met Claude at the end of 1948, and then in 49 they were already married. So here's a picture of her, of Betty. Betty had grown up in New Jersey, in Staten Island, and joined Rutgers as a mathematician, was the first person in her family to go to college. And right after they got married, then she quit her job in Bell Labs, even though she enjoyed it quite a bit. And then, of course, we come to the magical year of 1948. And a lot of things happened in that year. Among others, in Murray Hill, these three people invented the transistor. And from our own viewpoint, these things are all very important, but not more than this. So yeah, so as you can see, Claude mentions Nyquist and Hartley. And in his usual modest way, he says, in the present paper, we will extend the theory, okay? It's very self-effacing to say that he's extending a theory when he's actually coming up with a completely brand new theory. So most of the advances in science come in the footsteps of many others and so on. But really, this is one of the few cases where a whole discipline has a birthday, because this was so different from what everyone else had been thinking about. And you know, if you're not in information theory, this paper is still very much alive today. And every time technology improves and we have more and more engineering advances, this paper becomes more and more relevant, as opposed to most of the stuff that happens in engineering that has very limited shelf life. So anyway, I don't want to spend too much time on the technical aspects, but as you can see, the idea here is to bring a mathematical theory to the whole discipline of communication. So mathematize these problems of designing systems that up until then had been designed in a very ad hoc fashion. See if we can come up with ways of designing those systems as the result of an optimization problem. Now, as I mentioned before, that was not a new idea. For example, the match filter I mentioned that had been obtained as the result of a maximal SNR problem. The winner filter, Kolmogorov filter, that was also the result of mathematizing a certain estimation problem. But what was very interesting here is that he was actually coming up with the best you can do, what we call the fundamental limit. What is the best performance that one could achieve if we didn't have any constraint on the complexity, okay? Now, the brilliant stroke is that he was able to do that without actually knowing how to implement the solution. So he found out what are the fundamental limits without actually knowing what algorithms would achieve those limits. And he did that thanks to the probabilistic method, what we now call the probabilistic method, which is, of course, a very important tool in theoretical computer science, or what we call random coding. So really, the first non-trivial instance of that method is in this paper. Erdos, who the computer scientists like to attribute the probabilistic method, at about the same time, wrote a paper that if you read it in thinking about it, you can see that that is the seed of the probabilistic method, but it's in a much more narrow sense. Okay, so then that paper was reprinted by University of Illinois Press with a slight change in the title. Now it became The Mathematical Theory of Communication. And in addition to Shannon's paper, there was a small tutorial by Warren Weaver, the one who had gotten him the job in Princeton. And by that time, I think he was already the head of the Rockefeller Institution. That paper, to be honest with you, didn't really do much to explain information theory to the public, because already Shannon's paper itself is very easy to read by a non-expert. So he took care of writing it in a way that would be very accessible to a wide audience, without necessarily putting all the epsilons and deltas in all the results. So a lot of the stuff that he has there, he doesn't actually prove it, but in fact, he was never actually proven wrong in any of the things that he said in that paper. So maybe that's also accounts for the fact that since his paper was so easy to read, in fact, it became an instant hit. So many people outside communications, thought of an information theory as the theory of everything. So, this is a tool that we can use for all sorts of different things in all sorts of disciplines, psychology and linguistics and so on. And Claude, in fact, wrote a paper called The Bandwagon, where he was decrying this tendency of just playing with words and trying to apply these to all sorts of things. So nowadays, we in information theory, in this community, we've always been very shy. We've always tried to err on the side of not stepping into other people's turf rather than the other way around, unlike computer science or physics. Nowadays there are indeed very nice applications of information measures from genetics, biology, things like that, and also linguistics and so on. But of course, where it really has shined and been a resounding success story has been in its natural habitat, which is communications, transmission, and compression of information. Not to say that it has been a monotonically increasing function, the fact that we've enjoyed this high reputation of Shannon's theory. In fact, it has had its ups and downs, because what Shannon promised in 1948 the fact that you had these fundamental limits, like the capacity or the minimum source coding rate at which you can compress a message. For quite some time, people were very skeptical because all the work that was going into the actual theory of building codes, of coming up with algorithms that would come close to Shannon's promised limit, was not being very successful. So there was a lot of very interesting work, primarily along the lines of generalizing the Hamming 7-4 code, beautiful geometric object. So people were trying to play that game. But that was a very different game from the game Shannon had set up. In essence, because Hamming's game is a game of a worst case model where you want to guarantee that you correct a certain number of errors, whereas Shannon was really more of an average case model. So for a long, long time, people were skeptical whether those Shannon limits were really relevant to practice or were like, the same limit that, okay, I know that we cannot go faster than the speed of light, but maybe if you work for Volkswagen, maybe that's not so, or even Ferrari, that's not so relevant, right? But it turned out that, yes, if you work for Qualcomm, you really are very interested in knowing what the capacity of a channel is. But that realization did not come until the 1990s. So it took a long time before people realized that, indeed, those limits, you can come very close to those limits with very reasonable complexity, essentially linear complexity. And that was really thanks to the turbo codes and also the low density parity check codes that had been invented here by Bob Gallagher, but kind of dismissed in the early 60s as not having very good performance complexity trade-off. But then later on, people realized that with a few tweaks, then those things were going to work beautifully. Always not trying to decode them optimally, but a suboptimal, judicious way in which you kind of divide and conquer is gonna do the job. Anyway, the 1950s, at the end of the 1940s, this was a very productive period in Claude's life. He published this paper in the proceedings of the IEEE right after the Bell System Technical Journal paper, also a very important paper, kind of introduces the geometric approach to digital communications. And then here you see a family tree. I said that Claude and Betty got married in 1949, and they had 3 children, and Andrew and Peggy are today in the audience. This was, as I said, a very productive period and reproductive period in Claude's life. So here you can see a paper he wrote with his boss's boss, Hendrik Bode. At that time, he was still a senior member, whereas Claude was already a fellow of the IRE, so he became already at a very young age, 33, a fellow of the IRE, thanks to his paper. So here we see him Bell Labs. This is his penchant for building machines, of course, continued, and this was a chess-playing machine that he built with Lasker in 1949. So it had a random element so that, of course, it was not designed to play a whole game, it was just with only a few pieces, but it had a random element so that you wouldn't get the same move always. And he built this Theseus, which was kind of like an artificial intelligence machine where this mouse would remember what was happening when it was going through this maze, and finally, after trial and error, then it would find the clear way to the exit. So he also had a humorous side. So he built this calculator in Roman numerals. Well, he didn't sell a lot of this. So remember that then these early computers always had an acronym ending with AC, like ENIAC. So he called that the throwback. Thrifty Roman numeral backward-looking computer. This is the ultimate machine. It's also called the useless machine or useless box. Actually, Claude, the way he built it was a coffin and with a switch, and then when you press the switch, then there is a hand of the cadaver that kind of says, "Leave me alone," and then goes back to the coffin. All right, so here's a letter he wrote to Hendrik Bode in 1956, and in this letter, this is the resignation letter, where he says that he's going to MIT. This is a long letter, and he says, I don't know whether this is still true now, but he says, well, the long vacations in MIT are exceedingly attractive, and the general feeling of freedom in hours of work. So, you know, he likes that. And at some point he says, well, you know, I'm excited about teaching, but maybe the novelty is going to wear off quickly, and indeed it did. So this is the house that Betty and Claude bought, and still belongs to the Shannon family. This house was built in the 19th century by a great-granddaughter of Thomas Jefferson. And here you can see a picture of the backyard with this mystic lake. And Claude and Betty built this cable car for the children to go from the house to the lake. And actually, they had famous neighbors. One of them was Land, the inventor of the Polaroid camera. And on the other side, right, the next door neighbor on the left, he was also a professor in this department, electrical engineering, very famous, also a National Medal of Science. And his brother was a developer in New York, and his nephew is Donald Trump. So Donald Trump was asked recently about nuclear weapons, and he said, well, I know a lot about nuclear weapons. And in fact, everything I know was because of my uncle, who was a genius, professor at MIT. And then I was interested, and I looked it up, and it turns out that his uncle was an expert on microwaves. So anyway, Claude, continued working very, very hard, and always writing papers by himself, tough papers. And if he could write one excellent paper, he wouldn't write two very good papers. So, for example, this one here kind of has a very famous result on the fact that feedback is useless when, as far as increasing capacity, when the channel has no memory. But he puts that result in the context of another problem that is a very, very tough problem. So he also became interested in portfolio issues, in mathematizing the idea of investing in the stock market. And he published some notes, but never any papers on this. And of course, the story is that he and Betty were very successful in investing in the stock market, but he always said that was more a matter of knowing where he was investing rather than really following any theory about technical analysis. Again, very important papers he wrote. He tried not to get influenced by other people. So, for example, one of the things that he didn't do in his 48 paper, which was a posteriori one of the key missing pieces, was what we call Fanos inequality, which connects the world of information measures with the world of error probability. And interestingly, later in papers that he wrote where he actually could have used that, he actually wasn't using Faneuil's inequality, he was just rederiving results by himself. So he always tried not to get too influenced by outside authors. Yeah, so, I don't want to spend too much time on any of these papers in particular, but let me just tell you that these are all masterpieces and extremely good papers, even though, for a long time they were kind of underrated, perhaps because they are not so easy to read. They all contain highly non-trivial results. Interestingly, the Fourier paper talks about three very important pillars in information technology. One is the problem of transmitting data through noisy communication channels. The other one is the problem of lossless compression of data, for example, of texts and so on. And the other one is the problem of lossy compression, of turning pictures or audio or video into bits. And that paper, or that branch, that third branch, in the 1948 paper, he already has the answers, but he really does not elaborate how he actually got those answers. And so it took him 11 years, actually, until he wrote this extremely nice paper on the mathematics behind that whole theory. So that actually meant that this rate distortion theory branch of information theory always has lagged the channel coding branch of information theory by about 10 years or so. And still, the gap between theory and practice here is much higher than the gap between theory and practice in the other two. So, people who are experts on this, their goal is to fool the human ear and the human eye, and we still don't understand that very well. So this comes to 1960. Claude is 44 years old, and this is his last single-author paper, a paper that actually introduces a whole subject of multi-user information theory. And at the end of the paper, he promises that he has found a very nice solution to what we call now the multiple access channel. He says, I'll publish another paper with the solution, but he actually never did. So the solution was not found until 11 years later. He did publish a paper with Shannon, with Gallagher and Berlekamp in the 1960s. But at that point, he quickly became less interested in teaching and in doing research. But his stature in the general, in the general public was, he had achieved, an icon status. So here we have a photograph by probably the most famous photographer in history that appeared in Vogue magazine. So imagine now a professor of MIT appearing in Vogue magazine. Or in Life magazine, another very famous photographer, Alfred Eisenstadt. And here's a picture of Claude playing chess against the Russian world champion, Botvinnik. In fact, Claude had written one of the first papers that talks about how to program machines in order to play chess. And people who are in that line of inquiry, they say that the principles on which Deep Blue is based, in fact, come from Shannon's paper. In that paper, he computes the probability of beating Botvinnik with random play, and he estimates that it's about 10 to the minus 75. So this was a visit of Claude to the Soviet Union. I should make a parenthesis here, and it's quite ironic that the reception that Shannon got from mathematicians in the US was quite cool. There was a review article by Doob, who was the dean of probabilists in America, that was quite critical of the level of rigor of the 1948 paper. And instead, in contrast, Andrei Kolmogorov in the Soviet Union immediately recognized how important Shannon's paper was. He started a long and very distinguished school of mathematics of information theory in the Soviet Union. So they invited Claude at some point to visit. And here's Claude and Betty with a bunch of musical instruments that they bought in Moscow with some rubles they got because they reprinted Claude's book in Russian. Here's another picture of him with the reliability function. We still don't know. This is upper and lower bounds. There's still some area there that we don't know here. So if any of you are interested, see Professor Polyansky. He can give you some ideas. All right, so, at this point, it was harvest time. He was getting a lot of awards and so on. I've listed here many honorary doctorates, in particular Princeton, National Medal of Science from President Johnson, as I said, the IEEE Medal of Honor, the Harvey Prize from the Technion, the Claude Shannon Award. He was the first one to receive. At that time, it was not called the Shannon Award. It was called the Shannon Lecture. The Shannon Lecture, and then in '95, retroactively, all the people who gave Shannon lectures were given the Shannon Award. And anyway, so here's a picture of this. I think was what the room where he had a lot of his gadgets and toys. And this person in particular here is Hilbert, David Hilbert. Yeah, he looks very much like James Joyce, who was also a hero of Claude. So he liked globes, he liked roulette wheels, he liked chess sets, so you see some of them. And apparently he also liked skeletons. And also one of his passions is early on, Betty gave him for his birthday a unicycle, and then he loved riding on unicycles, designing unicycles that had all sort of weird features like no pedals, no seat, not simultaneously, and square tires also. And then he also became interested in juggling. So he actually devised the fundamental limits of juggling. So he gave a formula for number of balls in the air, and one of the parameters is how many hands you have. He sent it to Scientific American, but he never got around to actually
constructing these juggling clowns led another mathematician, Dr. Claude Shannon, to become more intrigued with the problem of building a real juggling machine.
Machines like this only give the illusion of juggling. They have a complex mechanism, but the props, as we call them, never actually leave the ground. They're all held up by black wires and so on. And so far as I know, no one had ever built a real juggling machine. It occurred to me that I would like to try to do that.
The juggler's skills cannot yet be engineered. To build a device that could imitate him, Dr. Shannon had to simplify the problem.
When you bounce juggle, the ball is almost stationary, so you're not wasting much energy. All you have to do is give it a little toss like that, and then we'll come back to the same height. So you're saving a lot of energy. One can see how easy it is. Another aspect of this is that the ball is moving slowly when you catch it.
W.C. Fields, Dr. Shannon's juggling machine, lacks feedback. It can't sense variations in its toss or catch, and so must rely only on the repetitive dynamics of the ball's fall and bounce in order to maintain its rhythmical cascade. chip-like hands help make up for the lack of feedback, catching and funneling the balls back onto the optimum path. The mathematical analysis of juggling.
Okay. A machine to build, to solve Rubik's Cube. I think this is in the MIT Museum. And then after a long battle with Alzheimer's disease, he died at the age of 84. So he's buried in Mount Auburn Cemetery, not far from here. If you ever go there, look on the other side of the tombstone. There is the formula for entropy there. So you have one of these here, of course, in this building. This is Betty with the statue in Gaylord. There are also other copies in AT&T Labs, in Bell Labs, in the University of Michigan, and another one in UCSD. So I think those are all the copies. So that's another view of the square in Gaylord, where the statue is. And then for his anniversary, at the end of April, there was this conference in Bell Labs on the future of the information age. And then they unveiled a plaque, which is like the twin plaque to the one we're going to see in a few minutes. And postage stamp from the Republic of Macedonia. We tried to get one from the United States, but somehow we were not successful. And then, of course, you may have seen the Google Doodle on that day. So anyway, I know I'm really running out of time. So thank you all for your attention. And we do hope that, now with all this effort, we're also filming a documentary, which is going to be like a 1-hour documentary. The Shannon family were kind enough to let us interview them and film in their house and so on. And we have also interviewed already quite a number of people who knew him and so on. So hopefully, with all these efforts, he will become, again, well known to the general public in the way that he was in the post-war era. Because he really deserves to be much better known, given that everything that we have nowadays in wireless technology, information technology, and so on really goes back to his 1948 work. And with that, I conclude.
Upstairs, we won't let you grab and hold back the speaker.
Yes.
Say something about the relationship of Shannon with Norbert Wiener?
Yes. So interesting. So some people even think that Claude was a disciple of Wiener and so on. He really wasn't. He was very gracious. In his 1948 paper, in the acknowledgement, says that he's really influenced by Wiener's treatment of the problems of noise and so on, and somehow Norbert Wiener tried to get a lot of credit that he didn't really deserve for information theory. So some people believe that Shannon is to digital what Wiener is to analog, but don't believe a word of that. So really, there is no evidence that Wiener ever really understood or even read the 1948 paper. What Wiener did was one thing. At the same time, 1948, he published a bestseller with quite a few equations called Cybernetics. That became, he sold quite a few tens of thousands of copies. And in that paper, he says, von Neumann has told me that the integral of a probability density function times its logarithm is an interesting thing to do because it somehow measures uncertainty. And he says, okay, let me minimize this. He didn't have the minus sign. Let me minimize this subject to a variance constraint. And then he got the Gaussian distribution. And then he said, well, let me also look at the difference between that and its conditional version, and then he got this log 1 plus SNR formula. But he really never had any connection between those information measures and coding problems. So that's what it was missing. But he was not shy about trying to get credit. He would say, the information theory due to Shannon and myself and things like that. So yeah, I think Claude had a lot of patience with Norbert Wiener. But on the other hand, Bob Fano, for example, told me that here in MIT, they were very keen on being very nice with Wiener. So for example, Fano wrote an article also a few years later, and he also credits information theory to Wiener and Shannon, which from a person who knows a lot about the genesis of the field is a bit strange. But yeah, so that it's really Wiener's role in information theory is much less than maybe what a lot of people believe.